All right, so let's start with the cornerstone of today's conversation: voltage, current, and resistance. These three are like the holy trinity of electronics, you know? And I think one of the easiest ways to explain them is with a water analogy. So let's imagine a pipe system. Voltage, first off, is like the water pressure in that pipe. It's the force that pushes water, or in this case, electrons, through the system. If you've ever held a garden hose, you can feel the pressure when water shoots out faster. That's voltage. It's measured in volts, or simply V. Now, current is the amount of water, or again, electrons, flowing through the pipe per second. It's like the volume of water moving through the hose. A narrower pipe with the same pressure lets less water flow through, right? Current works the same way, and we measure it in amperes, or amps. Finally, resistance is the pipe's diameter, or any sort of blockage that slows the flow of water down. Resistance determines how much current can make its way through the circuit, and we measure that in ohms. If you've ever kinked a hose to stop the flow, you've created resistance. Simple as that. Now let's bring these ideas to life with a real-world example. Imagine you've got a circuit set up with a 9V battery, an LED light, and a resistor. The 9V battery provides the pressure. That's the voltage. The LED is where the flow of electrons, current, goes to light it up. And the resistor? That's there to make sure the LED doesn't get overwhelmed by too much flow, which could burn it out. Here's how it works. The higher the voltage, the harder the push on the current through the LED. But the resistor steps in to slow things down just enough to keep everything balanced. Without it, the LED could overheat and stop working altogether. It's all about keeping the resistance at the right level for the circuit to work efficiently. And of course, this isn't just limited to a small LED project. This principle powers so much of our daily tech. Your smartphone, your remote controls, any device with a battery relies on this balance of voltage, current, and resistance to function properly. A smartphone battery, for instance, might deliver a steady voltage to keep all those components inside running smoothly without overheating. So that's really the big idea here. Voltage gives the push, current is the flow, and resistance keeps everything under control. Together, they're what make electronics tick, from the simplest circuits to the most complex devices. So, now that we've covered voltage, current, and resistance, it's time to tie them all together with a little something called Ohm's law. This is one of the most fundamental tools in electronics, and it's really not as intimidating as it sounds. It's just a straightforward equation. Voltage equals current multiplied by resistance. Or written out, it's V equals I times R. Here's the beauty of it. If we know two of those values, we can figure out the third. Let's break it down with a simple household example. Imagine your kitchen wiring. Say a light fixture isn't working. You've measured the voltage from the circuit breaker to the fixture, and it's fine, but the bulb isn't lighting up. Using Ohm's law, you could determine if the issue lies in the wiring's resistance or the lack of current to the bulb. And it's not just theoretical. Let's actually calculate something. Suppose you're working with a flashlight and a 1.5V battery. If one part of the flashlight circuit has a resistance of 3 ohms, how much current is flowing? Well, using our formula I equals V divided by R, that's 1.5 volts divided by 3 ohms, which gives us a current of 0.5 amps. That's half an amp flowing through the flashlight circuit. Now let's flip it around. Say the current is fixed at 2 amps, and the voltage supply is 12 volts, like in some car wiring. How much resistance would keep things balanced? Rearrange Ohm's law to R equals V divided by I. So 12 volts divided by 2 amps gives you a resistance of 6 ohms. Simple enough, right? What makes Ohm's law so powerful is how it simplifies problem solving. It's like having a diagnostic tool built right into your understanding of circuits. When you troubleshoot something, whether it's a flickering light bulb at home or a connection in a DIY electronics project, you're likely using the principles behind Ohm's law, even if you don't realize it. So keep this equation in your tool belt. V equals I times R. It's your shortcut to understanding how electricity behaves, whether you're dealing with small gadgets or the big wires in a wall circuit. It clears away guesswork and makes problem solving so much easier. All right, we've talked about voltage, current, and resistance, and seen how they're tied together through Ohm's law. Now let's tackle power, a concept that shows us just how much work we can get out of electricity. At its core, power is the rate at which electrical energy is being used or transferred. And the equation? It's just P equals V times I. Power equals voltage multiplied by current. Pretty straightforward, right? Here's an example you can picture at home. A light bulb. The wattage rating on a light bulb, say 60 watts or 100 watts, tells you the power it consumes when it's turned on. That wattage comes from multiplying the voltage from your wall outlet, which is normally around 120 volts in the US, by the current flowing through the bulb. That's why different bulbs produce varying levels of brightness. More power means more light output, but power doesn't just stop at light bulbs. Think about your phone charger. If one charger sends out higher voltage at the same current than another, it's going to charge your phone faster because it's delivering more power. This is why fast chargers work so well. They're designed to balance voltage and current in a way that speeds things up without causing overheating. Now let's tie this back to resistance and Ohm's law. Imagine adjusting the brightness of an LED in one of your projects. Increasing the voltage while keeping resistance constant will boost the current, and that means more power is being delivered to the LED, making it shine brighter. On the flip side, introducing more resistance cuts the current, reducing power and dimming the light. It's all about finding that right balance for the effect you want. Here's another relatable one. Volume levels on a speaker. Turning up the dial increases the voltage going to the speaker, and with the resistance fixed, you get more current flowing through. That, in turn, delivers more power and more sound. But crank it too high, and you risk overloading the system. So once again, balance is key. And don't just take my word for it. One of the best ways to feel the power of these principles is to put them into action. Try building a simple circuit at home with some basic components: a little battery, an LED, a variable resistor. Then tweak the resistance or voltage and watch what happens to the brightness of the LED. It's like having a front row seat to the interplay of electricity at work. Plus, experimenting like this is a great way to make these ideas stick. So there you have it, a full circle look at voltage, current, resistance, and power, all woven together by Ohm's law. These concepts aren't just theoretical. They form the heartbeat of nearly every electronic device in your life. From the LED on your TV remote to the circuits driving your car, it all begins right here. And that's all for today's episode. Thanks for tuning in to Mastering Voltage, Current, and Ohm's Law. Keep experimenting, keep asking questions, and most importantly, keep that curiosity charged up. Until next time, I'm Eric Marquette. Stay curious, and I'll catch you in the next one.